Hello everyone, good morning. My name is Alif Adiyat and I'm here to present to you the mathematics for economics midterm problem that was given to us. And yeah, let's get into it. So the problem is the model of discriminating monopoly with an output quota show that the marginal cost if the marginal cost of production is constant, that there is no effect on the position of quota 2 on price. Show there's no effect at the position of the quota 2 in country 2 on price and output in country 1. Explain this result. So the objectives of this problem is to show that Q2 will not affect, or the change in Q2 will not affect the P1 optimum and the Q1 optimum if marginal cost is constant. And how could this happen? So before we get into this, let me clarify that P is price and that Q is quantity. Number 1 and 2 represent the country 1 and 2 respectively. We note that the goal here is to maximize the profit, and marginal cost is constant and noted by C. See right here. The maximization profit function is max P times max P Q1 Q2 is equals to the total price minus total cost. You know the total price is P1 for country 1 times Q1, this for the country 1, plus P2 times Q2 for the country 2, minus the constant marginal cost times quantity 1 plus quantity 2. So this we could say the profit function. Now after we have the profit function, we'll derive it and get the first order condition for it. Now why does that happen? Because in order to maximize or minimize a value or a function, we need to get the first condition of it. We get the first condition as dou p over dou q1 equals to dou over dou q1 times the price times the profit function. That's the profit function right here. Now, what's happening here is that dou over dou q1 is inserted to the p1 times q1. So if you see here, there dou p1 over dou q1, so I said dou p1 over dou q1 times q1, then plus dou q1, see, go right here, dou q1 over dou q1 times p1. So it's the other way around. So we're gonna take turns and multiplying it. Then plus right here we go to p2. So dou over dou q1 times dou over times q2. Then sorry, not p1 here. So dou p2 over dou q1 times q2 plus dou q2 over dou q1 times p2. And minus, if you see here, C times Q and C times Q2. So minus dQ1 C over dou Q1 plus dou Q2 C over dou Q1. And we're gonna leave the front here just stay the same. But if you pay attention here, dou Q1 over dou Q1 is 1 times P1. So it's gonna plus P1 right here. And dou p2 over dou q1, there are nothing that we can derive here, so it's equals to 0 plus dou q2 over dou q1 plus q2 is same. There are no derivation here, so it's 0. So we get p1 plus 0, so we got dou p1 over dou q1 key plus p1 plus 0 0 minus, we got dou q1 over dou q1 is 1 times c, so minus c plus dou q2 over dou q1, there are nothing derivation, so it's 0 right here. Yeah, so if it's 0, because this is for the quantity 2, whereas this is the 1, so we get only minus plus 0, so we get dou p1 over dou q1 times q1 plus p1 minus c. We'll need this because we're counting for the optimization of quantity 1 and country 1. We'll do the exact same thing for the profit function for in regard of Q2 right here. The same exact thing. I'm just gonna concise it a little bit, but we will use the same method, the same steps, so it will result in the same, almost identical. It's only change in number here, only in 2 right here. So we'll get this dou p over dou q1 and dou p over dou q2. That's the first order condition. Now, what will happen if quota is imposed on Q2? When quota is imposed on Q2, remember that the optimization for dou Q2 is this. When quota is imposed on Q2, the function of dou profit over dou Q2, written from the first order condition, will no longer satisfy or met. Why is that? It is because Q2 has changed, so it's not equal to this anymore. Yeah, but the first condition, not the first condition, but the dou profit over dou Q1, the function for that will not be affected. It will remain the same. It will stay the same. Why? Because when quota is being imposed on Q2, it will only affect it changed the Q2. But if you see here on the first equation, there are no Q2 anywhere near here. There are no Q2 here, no Q2 here, no Q2 here. So making conclusion from that fact, I concluded that Q2 will not affect the ability of country 1 in maximizing the quantity of products or the price of the product. So quota imposed on Q2, since the equation does have the Q2 variable, so we can conclude that Q1 optimum and P1 optimum won't be changed or affected by the quota imposed on Q2. That's why. So we already explained how this could happen, and we explained that if marginal we prove that if marginal cost is constant, that if marginal cost is constant, that Q2 quota imposed on Q2 will not affect the price and output in country 1. Moving on to the second problem here, is about the utility function, optimizing the utility function. We got the utility function here right here, where C1 and C2 are interpreted as minimum amounts of the goods required for subsistence. We need to derive the demand function, discard their properties, and compare them with the demand function derived in the Cobb-Douglas. So we need to remember, when maximizing or minimizing utility function, we make utility function as the objective or as the subject. So this is the subject that we're going to maximize, and the consumer income as the constraint. So the only thing that limits the utility function is the income of the consumer or the individual. The income function is y, or you can use I or m. In this case, I use y. So y is equals to p1 times x1 plus p2 times x2. Here's the budget. Here you can see the income or the budget constraint. Now we need to derive a demand function. How are we going to do that? When we find the x1, x2, we're actually solving the demand function. So another way, if we get x1, x2, we get the demand function for x1 and we get the demand function for x2. Now, how are we going to do that? Remember that it's the Lagrange function. This is the utility one, and this is the constraint. So we're just gonna times lambda, lambda to the constraint. So we get this right here. Then we derive to the respect of x1 and to derive to the respect of x2. So this for the respect of x1, we get this value right here, and this for x2, we get value right here. And not to forget, not to forget to derive to the respect of lambda. So we just remove the lambda from the constraint right here. After that, we're gonna make lambda right here as the subject. Yeah. So we're gonna make lambda right here as the subject. If you don't mind. So we're gonna make lambda properly. If I'm doing this, lambda is equals to lambda is equals to. Sorry, a bit messed up. Or yeah, I'm just gonna. minus a times x1 minus c1 a1 times x2 minus c2, not that redo, sorry, c2 to the power of 1 minus alpha and over e1. Okay, we do the same thing as for this. We make lambda as a subject right here. After we do that, what we're gonna do is, let me just clear this up. How do I clear this? Okay, clear all drawings. We got sorry. See, we got with p1 right here, right? And p2 later. So we're gonna after lambda equals to lambda. Sorry, I'm gonna clear. When lambda is equals to lambda, we get p1 over p2. We're gonna get this value right here. Then we're gonna solve for x2. Why are we gonna solve for x2? Let me just move this out of the way. Why are we gonna solve for x2? Because later we're gonna put x2 to the lambda equation and solve for x1. So I'm gonna next step. Wait, let me just put next. All right, sorry about that. Did and clear all my drawings. All right, and so substitute the x2. We'll get the x2 right here. Substitute the x2 to the lambda function or lambda derivation. Got p1 plus p2 x2 is 0. X2 right here. So we're gonna input. It's gonna move out this right. We're gonna input p1 x1 plus p2 times x2. I put y here just for my convenience, so it's just a bit tidier here. So we get the idea. We get put x2, then we operate the things, then we're gonna solve for x1 right here. We're not solving for x1. When we come to right here, we're gonna solve for x1. So we make x1 as a subject. We get this value. The squared function right here is the demand function for x1. All right, this demand function for x1. Remember that. So after we get demand function for x1, we're gonna put it back to right here. So you get the x1 right here. We're just gonna put the value of x1 to this. Okay, I'm gonna put x1 minus blah 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 blah. We're gonna put to the x2 right here. X2, I gotta just put the see the x1 here. We're gonna put it the x1. We're gonna get this equation. It's a bit long if I'm gonna explain it one by one, but later we will get x2 equals to this value right here. This demand function for x2. So what affect x1, x2 the alpha will affect the x1, x2 demand function. The price of goods will affect it as well. The C is the amount of good, or not the amount, the minimum amount of goods that can be required, and the income right here. So see the income, see the price of goods one, price goods two will affect. Now, what is the properties of or characteristic of demand function? Demand function are single value. Means a single value price and income where quantity will be demanded for a fixed income and price. Is correlated with the strict quasi-concavity of the utility function. The second is the demand function is homogeneous of degree 0 is be off right here. Of degree 0 in price and income. So what it means, if price and income fall or rises proportionally, the consumer behavior or the demand for goods for this consumer will not change. It will not change. So the consumer or the individual will not act as he or she is poorer or richer. It will stay the exact same and the demand will be the same. So next, now we get to compare it to the Douglas function, the Cobb-Douglas function. In the Cobb-Douglas, see that we need to find the marginal utility of x1 and the marginal utility of x2. How are we going to do that? We're going to do that by deriving it to the respect of x1 and x2. Also, we got the marginal utility of x1 over p1 and equals to marginal utility of x2 over p2. If you notice here, so this the when we're inputting the value. If you notice here, p1 over p2 is the exact same method or steps are taken in the Lagrange function. So later we're going to solve for x2, but I bet you that the result will be the same, since so I can conclude that Cobb-Douglas method or the Lagrange structure are sufficient in creating, maximizing, or minimizing utility function. So next, see, we find the x2 here, we find the x2 right here. So we're gonna put it back to constraint. Oh yes, we get the x2. Sorry, we get the x2 is right here first. We get the x2, then put the x2 back. Yeah, we gotta put the sorry. So we get the x1 right here. We get the x1 right here. When we put it back to constraint, get x2, we get the x1. Then we're gonna put x1 back to the x2. So we get put x1 right here, and we get the x2 value, same like Lagrange, the exact same like Lagrange. Moving on to question number 3, we are required to solve the minimization problem of this firm function or firm production function with this constraint, where R is raw material, L is labor, K capital. The production function under this problem. So the objective of this question is to derive and comprehend the production function of the given minimization problem. Using the Kuhn-Tucker condition, we're gonna use the derivate all the variables. Since we have 3 variables right here from the function and 1 from the lambda or the constraint, so we're gonna do like a power do function over lambda, the respect of lambda, the respect of L, then the respect of K, and the respect of R. And the last but not least, with the respect of lambda. And we get this value right here. Remember that how in Lagrange we need to equals lambda, but since we got 3 right here, so we need to do it almost 3 times. Yeah, we're gonna do it 3 times. We're gonna equate lambda of equation 1 to lambda of equation 2. Then we're gonna do equation 3 to the equation 1. So you see right here, we take the lambda for equation 1 and equate the equation 2. See, lambda 1 and lambda 2, not literally lambda, but lambda from equation 1. So we get right here, if we make lambda subject, we'll get W over this value right here equals to R over this value right here. And if you simplify right here, you can see you can cancel out each of the LBK. If you cancel out all of the LBK, you get W over R equals 1 minus B. And for the second and third equation, you get R over this value equals V over this value. When it's simplified again, you get R over V equals RBC over A times LBK. And the third and first one, we get V over this value and W over this value. When it's simplified, we get W over V times C times LBK times R to the power of A over A plus LBK to the power of C times R to the power of A minus 1. So we get 3 equations. We're aiming to solve for LBK to the power of C. Or yeah, we're gonna have LBK to be later put back in the constraint. What's the constraint again? Let me show you the constraint again. See, this is the constraint. We're gonna substitute this later. Yeah? So I'm gonna use the second and the first, knowing that the first equation derived that W over R is equals 1 over B. This should be not this kind of R, but more of this kind of R. It's not this kind of R, yeah. These only capital R, not capital. I mean the lowercase r, right? So R equals to WB. So we're gonna put R back right here, yeah. This is the R here. We're gonna substitute by WB. Then WB over V equals to RBC over A times LBK. Remember, we got B right here, so we cancel out the B, we cancel out the B. And we get WA, we just cross multiply WA times LBK, L plus BK equals to VRC. Now we'll take this, I'm just gonna clear this. Now we'll take this value right here, we cross multiply it and we put it just right over here. Put it right over here, and we're gonna minus it to this value right here. What will get us is the we'll remove for not unnecessary variable. So we get R minus W times A times L plus BK equals to VRC times 1 minus B. Once we get it sorted, remember that we're trying to find LBK. We're trying to find LBK, L plus BK. So what we're gonna do is we're gonna move R to here. So later I'm gonna show you in the next slide. So we're gonna move R to the other side. We're gonna just times it later. So I'm gonna move it right there. Okay, and clear all this. So remember the constraint. Get R right here. Get R. We're gonna move it right here later. And we got, so when we put LBK, yeah, we're gonna put LBK. Remember, we still got C here, so we're gonna move it to the front as well. So R, just the capital R, to the power of A plus C, and to the power of A plus C times VC over A. VC times B minus 1 over A minus R minus W. Okay, that is more than or equals to Y. And we're gonna make R, because the production function R is, if I'm not mistaken, R is the capital, or not the capital, but R is the raw material. R is gonna be greater than this value. We got this product function. So we derive that by using this function right here, but by inputting the correct amount of prices of labor, not labor. Let me see what alpha again. Alpha is not between LR capital. Okay, so when computing the right amount of prices for each of the variable that was mentioned earlier, we're gonna maximize R. So that's the end of the PowerPoint, the end of my explanation. I hope you enjoyed it. I hope everything makes sense. Have a good one. Stay healthy. Don't forget to wear your mask, and see you on the next occasion. Bye bye.